Hi, good evening, everyone. I'm David Hampson, president of the Aero Club of New England, the first Aero Club in the Americas, and would like to welcome you all to the presentation this evening with Peter Schmidt. Before we get started, I just wanted to introduce Peter. I just want to mention a couple of things. During our presentation tonight, if you have any questions, Peter's happy to answer them during the course of the seminar. So just type them into the chat box, and our secretary Keith will be moderating those, and we'll pose those questions to Peter as we go along. And I just wanted to also let everybody know that while this is a virtual event, as a club, we are looking at incorporating some in-person events in the near future as well. And we look forward to this year providing all our membership with the best of both worlds, providing some continual virtual content along with in-person events as well. And I'll make a couple announcements of some upcoming events at the end of our presentation tonight. But I'm now going to introduce our speaker tonight, who we're very fortunate to have with us and giving us time tonight to tell us about the exciting developments at his company, Transcend Air. And Peter Schmidt, who I've known for a number of years, is co-founder and chief operating officer of Transcend Air. And he's a very experienced entrepreneur with executive, startup turnaround, and large enterprise experience. And he's had a number of aviation roles, including as a UAS test pilot, president and CEO of Linear Air, which is an Eclipse 500 operator, and Part 135 online charter marketplace. He's been the COO of Jet Advisors, the business aviation consultancy, and a senior vice president of the National Aviation Academy, the second largest Part 147 aviation mechanic school in the U.S. In his pre-aviation career, Peter also led several networking and embedded systems companies in a variety of executive roles. And Peter is not just in aviation from a business perspective, but he enjoys it recreationally as well. He's a very accomplished aerobatic pilot and previously owned his own Pitts aircraft, which I'm sure he'll tell us a bit about as well. And Peter's educational background includes his undergrad in computer science and master's in management, both at MIT. He currently serves as the chair of the Electric Flight Test Committee of the Electrical Vertical Takeoff and Lift Flight Test Council. And without any further ado, then I will turn it over to Peter. Thank you, Peter.
Thank you, David. Appreciate the introduction. And I appreciate the invitation to present to ACON. So I'm looking forward to talking about Transcend Air and what we're trying to do. I am virtually sitting in the cabin of our Vy400R. That's the reserved edition, the VIP edition of our VTOL aircraft. And so let me dive in, share my screen, and tell you about the Vy400 and what we're doing here. So as you can see, the title of my presentation is the Vy400, VTOL now, E when ready. So what does that mean? Well, you guys may well have heard, because there's been a huge burst of publicity over the past few years about electric VTOL aircraft, or E-VTOL aircraft. And some of the leading names based on their funding to date are Volocopter, Archer, Lilium, and Joby. So I put this graphic together to kind of show you the difference between what their aircraft designs are being stated is capable of doing and what ours can do. So on the near axis, we have the distance, that's the range of the aircraft. And then on this axis, you have speed. And so you can see the Volocopter, which is an 18-rotor multi-copter drone-based aircraft, can only go 22 miles at 70 miles an hour. So that's this little dark orange slice. Archer, which came out of stealth mode earlier this year, has an aircraft that can go 60 miles at 150 miles an hour. So Lilium is claiming 155 miles at 175 miles an hour. And then there's Joby, who say they can go 150 miles at 200 miles an hour. So these are limited range aircraft, and that's because they are trying to be all electric powered. Meanwhile, our aircraft, which uses a turboshaft jet engine, will take you 500 miles at 400 miles an hour or more. So we like to say that the Vy400 is using proven technology to build a disruptive aircraft. And disruptive of what? Well, disruptive in entrepreneurial terms. Disruptive of existing markets. So we're going after fast, convenient, affordable regional air mobility. So what does fast mean? Well, 405 miles an hour, 352 knots, 652 kph in airplane mode with the wing tilted down. Convenient, Well, one of the key things I learned at Linear Air is activating travel demand on aircraft at this scale using reliever airports is really challenging. We tried very hard. And what it comes down to is there just aren't enough people living around any given reliever airport to let you fill the seats, offer a dense schedule, and keep them full. VTOL is the key to unlocking the center of cities. We can operate out of city centers, and obviously that's where all the people are. It's like what Willie Sutton said when they asked him, why do you rob banks? He's like, well, that's where the money is. So why do we want to use VTOL to serve city centers? It's where the business travel demand is to start out with. And then affordable. Surprisingly, since we're all used to jet-powered aircraft, especially small ones at this scale that look cool, being expensive, it turns out that taking advantage of the VTOL architecture and going fast, we can use with a similar sized aircraft with one turbine to a Bell 407, we can cut the per mile direct operating costs 50% versus a Bell 407. And I'll talk some more about that. But even more importantly, affordable, we've designed a regional airline that will let us offer a $283 one-way ticket on average between Boston and New York, which I want to point out is less than taking an Uber to the airport, the Delta shuttle to LaGuardia, and an Uber to Manhattan. So that's what really gets me out of bed in the morning, is that this is going to be a mass market service that is going to be really nice. Some key facts about the aircraft: it's single pilot operation, has 5 passenger seats, so 6 places total. We use variable pitch propellers, but not constant speed in the usual way. They are, in fact, constant speed, but it turns out that changing the pitch of the propellers in ways different from how a turboprop works is important to managing transition. It is a tilt wing aircraft. I know it looks kind of like a mini V-22, and I'll explain the difference, but it avoids the V-22 tilt rotor complexity trap, which is very important to us. Has a single engine, so again, you see 2 propellers, you think it's a twin. Nope, it's a single. We use a mechanical gear train to drive those 2 propellers. It has a BRS, ballistic parachute system, so same as the Cirruses. And then you see an electric tail fan at the rear, which we use to give it pitch authority in the hover and helicopter mode. So that's some of the basics at a high level. Let me dive in here. So I'm assuming you have, in fact, heard about these eVTOLs. If you haven't, then my apologies for these next couple slides. But I've learned from talking about our aircraft over the past several years that everybody has a lot of built-in assumptions from what they've heard about eVTOLs, and I need to deprogram you from those assumptions in order for you to appreciate this aircraft. So this is a projection of battery capacity based on historical trends. So in the second half of the 20th century, batteries grew at 3% a year. That's the red line. When lithium-ion batteries first came out, there was a decade where they grew at 8% a year. That's the yellow line. And then there was a period where NiCad batteries grew at 5% a year. So depending on which growth curve you want to project for where we are today into the future, you get different time frames before batteries are good enough that you could fly a high-speed mission with them and get some range. And that's approximately 1,000 watt-hours per kilogram, that green line there. So you see it's 2041 until batteries will be good enough where we might consider an all-electric Vy400. So our position is that we don't want to wait 20 years. We've got an aircraft design we can build now, we can start selling now. So our position is sell aircraft now, electrify later. And if you look at our business projections, we project that we can sell $58 billion worth of Vys in the next 20 years. That's the actual marketing and unit shipments ramp-up graph there overlaid on the battery graph. So we're not willing to wait for batteries to get good enough for our city-to-city mission. So I mentioned that it looks kind of like a V-22. So how does it compare to tilt rotors? Tilt rotors are the only VTOL aircraft that are flying right now, and the V-22 is the only one that's in service. I mean, the only VTOL ones that are not turbojet powered, not counting the Harrier and the F-35, or helicopters for that matter. So what about tilt rotors? Well, they're complex. If you look in the lower right-hand corner now, you see that's a helicopter rotor head. If you count the parts in that helicopter rotor head and compare that to a variable pitch propeller, there's more than 10 times as many mechanical parts in that rotor head. Whirling around, spinning, twisting, leading, lagging, flapping, you name it, in order to make a helicopter work. And what the V-22 is two helicopters that they've yoked together and made tilt sideways. It's a miracle of engineering that it works at all. But because of that complexity, it's expensive to operate. It was expensive to develop. And it doesn't have a great dispatch reliability and service. It's not where the Marines would really like it. And you know, what's the expense? Well, those are $71 million aircraft. And these drawings are all to scale, by the way, just to give you a sense of the very scale. Bell is in flight test with the V-280 Valor, which they have aimed at a new Army program. That's going to be a $30 to $50 million aircraft. It's a 33,000 pound gross weight. The V-22 is in the 50,000 pounds class. Then we get the Augusta Westland AW609. If its fuselage looks familiar, it was deliberately designed to be like a King Air. They sort of saw it as a tilt rotor King Air. That's going to be a $24 million aircraft. It's been under development for almost 20 years now, or maybe over 20 years. And again, it's just these things are wicked complicated. Meanwhile, our design comes in in airliner trim. That's what this blue and white livery means, at a price of about $3.5 million. So our design targets have been simplicity, reliability, maintainability, interoperability. That's one of the benefits of using Jet A instead of electricity. Affordability, adaptability, and upgradability. And what do I mean by upgradability? Well, the good news is, in that great and glorious day when batteries achieve a sufficient power and energy density, we will be able to take the turbine out of the aircraft here, just behind the wing. We'll be able to take the fuel tank out right here at the CG, replace the turbine with big electric motors, replace the fuel tank with batteries, and existing aircraft will become all electric. So, I mean, we do believe and agree that the eventual future of aviation is electric, but we think people are trying to build all electric aircraft right now are jumping the gun and are going to regret it. And we're not the only ones who agree with that. Abbott Aerospace Canada, which is a very well-respected aerospace consulting firm, analyzed 220 aerial urban mobility designs, so including Joby and Lilium and the other ones on that slide, and us. And they ranked us number one. So we're very pleased that other aerospace pros understand the value of what we're doing and why. And in fact, we've attracted an amazing team to the program. And it's all because when we talk to people who actually are familiar with aircraft manufacturing and real aerospace programs, they get why we've made the choices we do, agree with it, and then they want to be a part of it. So we've been very fortunate that way. So what is our mission? Our mission is to target already proven markets with a low-risk, high-technology readiness level design. All right, TRL is a NASA acronym. They have a standardized ranking, and it goes from 1 to 9. And the higher you are on a TRL ranking, the less technology risk there is in that part, that subsystem, or your aircraft. So we've designed an aircraft that's going to fill two proven market needs: VIP, rotorcraft transportation, and regional airline needs. We've worked very hard with our team of advisors and employees and consultants to make sure that this aircraft is both manufacturable and certifiable. It's going to be profitable for the manufacturer. It's going to be profitable for the operator. You'll see when I show you some more of the interior, it's going to be liked and trusted by passengers. And ultimately, what's most important is it's going to enable lower prices for aircraft and fares on the airline. This business part is not specifically about the aircraft itself, but the reason it's so important is that this is where Greg and I, my co-founder, started with Transcend. Some of you may be familiar with the Eclipse Very Light Jet and the Very Light Jet bubble of the mid-2000s. I joined Linear Air picking up the pieces. Linear Air was the last independent operator of the Eclipse 500 standing back in 2010 when I joined. And the promise of the Very Light Jet age was based on NASA's Small Aircraft Transportation System concept, which sounds great. You could walk up to Hanscom or Beverly or Norwood or any reliever airport, and there'd be this really sophisticated twin jet sitting there waiting for you, all warm and ready to go, and you could fly off to wherever you want, and it would be inexpensive and affordable. Well, I spent 5 years at Linear Air proving that that's impossible. And that's one of the reasons why we're not interested in the urban air mobility application that the E-VTOL aircraft are targeting, because that's just a single city variant of this same problem. And I'm not here to talk about that in detail tonight, but what I am here is to try and explain to you guys, we had to find a business model where there'd be enough demand for the aircraft that it would be worth us quitting our day jobs and pursuing developing a whole new aircraft certification. And that's what this already proven markets is about. And that's what using proven technology is about. It's to contain the certification risk and know you're going to be able to sell aircraft and sell seats on aircraft afterwards. So Greg's quote here, it's a mistake to bet your success on future technology developed by someone else, right? We've got all the E-VTOL companies betting their success on unknown when it's going to happen battery improvements. We saw that with the very light jet bubble. Eclipse, their number one order set came from a company called Dayjet, which was another startup by Ed Yakabuchi. And his claim was that fancy math and software would let you optimize your fleet movements and make money. Well, it turns out it doesn't. There aren't enough people around these reliever airports to fill your seats, and so you're not going to be able to fill them, and then you won't make money, and it doesn't matter how fancy your math is. And I hear people nowadays, the vogue term is to say, well, we'll use AI. Well, no amount of AI and algorithms, and I say this as a guy who has an MIT computer science degree, is going to change the fact that there aren't nearly as many people living around Hanscom as there are around Logan. So you can't run a schedule. And that's my quote. I mean, I learned the hard way. If you haven't ever sold air travel, there are lots of reasonable sounding arguments about why people should buy it that turn out not to be true. And so my tenure at Linear Air was really just a succession of testing those and finding out they weren't actually true, sadly. So our program will succeed because there are 3 aircraft markets. 2 are already proven, the VIP helicopter disruption and regional airline service. And again, this is why we did it, and I'm motivating it to you because I want to give you hope that this cool aircraft will actually make it through certification into market, and you'll get to fly in it. So the simple math on our aircraft is it is half the acquisition price, 3 times the speed, and 1/4 the operating costs of a medium twin executive helicopter. So that's a 24x value increment, which is why we're going to disrupt the VIP helicopter market. So we think of the Vi as the world's fastest helicopter. And why is that? Well, there's no free lunches in engineering, and especially not in aircraft engineering. You've got to make trade-offs. And so the Vi has some real advantages. It's high speed. It's the highest speed aircraft on this list. It's faster than the King Air. It's faster than the Pilatus. And it's got cabin volume. It has nice big cabin volume. It has similar cabin volume to the King Air. Not as much as the Pilatus. That's the King. More than the Sikorsky S-76. A little bit less than the Leonardo AW139. And hugely more than the single-engine helicopters, 61 cubic feet and 84. I mean, the Vi is at 252. So what's our trade? Well, look at the range. In executive trim, as you see here with the big fuel tank, and with just a pilot and 1 passenger, it'll be able to go 550 miles with appropriate reserves. You look at the other helicopters, and they're like, nearly 400, little over 400 for the Sikorsky. So we're comparable to that, maybe a little bit better. Then you look at the Pilatus, over 2,000 miles. All right. So somebody who buys a Pilatus wants that range, and they're not going to buy a Vi instead, even though it's faster. We don't have the luggage carrying capacity, and we don't have the range. So we don't expect to really compete with fixed-wing turboprops at all. But we do expect to eat the lunch of these turbine helicopters, because in executive trim we're more than these list prices for the Bell and Airbus, but those are in standard trim. If you do executive trim on those, you get something that's going to end up similarly priced. And meanwhile, we're half the price of the executive helicopters. And the main reason for that is those are twins. They've got 2 engines that are similar to what we run just one of. And they need to for safety, because if they lose 1 engine, they want to be able to make an emergency landing on the remaining one, running at extra high power. We rely on the parachute for that. So you can see how all the aspects of the design come together to yield the benefits we're going after. And Keith, I'm not monitoring the chat, so if there are any questions at this point, I thought maybe I could pause for a second.
No, you're doing such a great job right now with providing information that we don't have any questions just yet, but people should enter them in the chat if they're interested.
Yeah, if anything comes up, please do. So it's not just us that think that it's great, or Abbott Aerospace that think the design is great. I'm pleased to say that we also won an award from the Robb Report, which is a luxury publishing empire, if you're not familiar. So we were awarded Best of the Best for VTOL concept for the Vy400R Reserved Edition. That's the VIP model. It also stands for Racing Inspired. can see the polished carbon fiber interior in here. And one of the things I really want to highlight as an aircraft feature is one of the benefits of the wing is cabin volume. So if you look at our club seating configuration, if David and I sat opposite each other in those seats and stretched our legs out, we wouldn't even be able to touch toes. And you compare that to the best of the best winner for helicopter, which was this beautiful Airbus ACH 130, the Aston Martin edition. And it has the same number of seats, by the way. It's a single engine turbine. But look at the legroom. I mean, that's worse than an airliner. That's the problem with helicopters, especially smaller ones. You have to fit all the mass underneath the rotor disc, and so you end up with no legroom. So for about the same price as this ACH 130, you can go 3 times faster with half the per mile operating costs and that kind of legroom. You can see why we're pretty bullish about disrupting the market. But what about this airline service I'm talking about? One of the questions that I get asked fairly frequently is, if this regional VTOL airline service is such a good idea, how come people don't do it with helicopters? Well, the reason is it's too expensive to do it with helicopters. And the reason it's too expensive to do it with helicopters is because they're slow. So I was talking about per mile operating costs. The Vi does the trip from Boston to New York in about 36 minutes. In a Bell 407, it's nearly an hour and a half, right? So even though the Bell burns less fuel per hour than the Vi does, the fact that it's so much slower means to accomplish the trip, it burns more than twice as much fuel. It puts more than twice as much wear on its engine. And so the DOC per mile is twice as high. And when you flow that through a typical Part 135 cost structure and pricing structure, which is what I've done in this example, I'm assuming all of these aircraft are being operated Part 135 commuter on a scheduled service. When you flow that all through, the ticket price you can charge ends up being up around $600. Another thing that hits you is that with an aircraft as fast as the Vi or even the Cessna and the Pilatus, you can run 4 round trips per day between Boston and New York. And you have to use 2 shifts of contract crew to do it, by the way, based on rest and duty regs for your ATP pilots or your commercial pilots. But you can get 4 round trips. The helicopters are slow enough that you can only get 3. And that missing that 4th round trip per day means that you're amortizing these ticket prices over lower capital utilization. So in business terms, it's just less efficient aircraft, and that ups your prices. So you'll see that the Vi falls between an airline at 7 days advance purchase and an airline at 2 days advance purchase. So we are down in the considered set. Your CFO would likely accept an expense report for our ticket price for a business trip. But what I learned at Linear Air, much to my chagrin and to dashing the hopes of people who think that a 60% reduction in operating costs means cracking open a big market. If your price is not lower than the airlines, they will not fly on you. There's no mass market at prices higher than the airline fares. And the reason for that is, unlike us pilots and aircraft fanatics, travelers only care about what they're going to do at their destination. They don't care about the aircraft. And the people paying their travel bills only care about minimizing that expense. So, I had a real life example where a friend of mine needed to do a pop-up trip to Montreal, he and another person from his company, and chartering a Linear Air Eclipse jet was actually less money than the last minute fares on Air Canada. And his company would not let him pay Linear Air less money than flying on Air Canada because they had such a strict no flying private policy. So they spent more money in order to protect what they saw as a critical expense saving policy for them. These aircraft, the King Air, the Pilatus, and the Cessna, one of the reasons they're more expensive, I mentioned, is that they have to use airports. And what's the disadvantage of using an airport? Well, in the case of our travel model, which is downtown to downtown, it's actually a pretty significant price to take an Uber out to a reliever airport or from a reliever airport into the city. So there are certainly cases where, if you lived near Hanscom and you had a meeting near White Plains or Teterboro, then in that case, a caravan would be cheaper than the Vi, right? Because your ground transportation cost wouldn't be amortized in. What I'm showing here is door-to-door time and door-to-door cost, including ground transportation. So, there are certainly trip classes where the VI would be more expensive. But on average, for the big bulk of travelers in the center of the city, we're going to win. Now, our design comes from a legacy of 16 flying prototypes that dates all the way back to the first napkin drawing, and there it is in 2009. Prior to co-founding Transcend Air with me, Greg, my CEO, he quit his day job and joined a guy named Oliver Garrow. Oliver is a VTOL inventor, and Greg saw some of these prototypes that Oliver had already developed and flown. He convinced Oliver to quit his day job, and they together built a 2,000-pound manned prototype aircraft, which is this one right here. So this is a 2,000-pound experimental. It's a tilt wing with 2 props, like the VI, but you'll see it has this box wing or Prandtl wing wrapped around it. And that design dates all the way back to Proto 8 here in 2013. So you see Proto 8 has the central tilt wing and the box wing around it. This is a 1/5 scale prototype aircraft, but that performed so well, that's what convinced Greg to partner with Oliver and fund the development of that 2,000-pound manned aircraft. And so this lineage of prototypes has been hugely educational and influential in our aircraft design. You can learn a lot from simulation, you can learn a lot from analysis, but you have to fly in order to see where reality really is. And with this lineage, I can say that the VI design benefits from the reality of flying more different types of electric VTOL aircraft than I think anyone else in the world, including NASA, by the way. So again, that's another reason why we're confident that we've got a real winner of a design here. And I should stress again, all of those on this page are electric aircraft. Our current 5th scale prototypes are electric. And as David said in my intro, I'm the chair of the Electric Flight Test Committee of the E-VTOL Flight Test Council, because we are actively flying electric aircraft now. It's convenient at the 5th scale to do that. So we know very well why electric aircraft limitations are strong right now, and that's why we're sticking to a turbine. So here's some examples of the 5th scale, and you can see some of our telemetry data from while it's out flying. And down in the lower left here, that's our Chief Software Officer, Bob Schulman, with one of the 5th scale prototypes up at ICAO headquarters in Montreal. We were invited to present at their Innovation Forum, which was really cool. Over here in the upper right, you can see a parachute test. Our 5th scale has a parachute, just like the full scale, and for similar reasons, for safety. These aircraft are pretty big. They're small UASs, which means they weigh just under 55 pounds. And that's a lot to come falling from the sky if there's a malfunction. So we have this parachute on there, and it'll be automatically deployed if the aircraft goes out of control, and we can manually deploy it with a radio signal. It uses, the Cirrus parachute uses a rocket to deploy it. We use a compressed CO2 canister that blows the packed parachute out of its container. So what that white puff is a puff of carbon dioxide smoke, and there's actually a little bit of bits of carbon dioxide snow flying out of there too, which I thought was kind of cool. And there's me standing with the two flying prototypes together. So again, we've learned a lot here, and we iterate through flight test, truck-based wind tunnel testing, X-plane flight simulation, and all sorts of analytical tools. And we don't believe one technique by itself, and it's not until we put something in the air that we really believe we have something. So before I dig into this, I wanted to be the cool teacher and show some videos. So I'm going to stop sharing this slide here for a second. I see a question. Jeff Ward, where are you in development of this aircraft? So we've been running what's effectively a 30-person R&D program for the past couple of years. And we've advanced into the preliminary design stage. And what we're doing now is we're conducting a significant fundraise that we expect to take us through completing the preliminary design, onto doing detailed design of both prototype aircraft and starting the certification track effort in parallel. And then we'll be feeding more flight test information from the prototypes into getting our certification track articles in shape and bringing up our production line and going to LRIP. So, if everything went perfectly, which it probably won't, but if everything went perfectly, we'd see entry into service in late 2024. So let me show you a video of what it looks like. I'll show you some X-plane simulation videos and one prototype flight test video here. So I'll start with the service video. Pull that up. There we go. So this is Manhattan to Boston. It is a commercial, so forgive me, but you also get to see all phases of flight, what it'll actually look like.
Peter, we're not getting the audio on that. Just a
Oh, you're
heads
not
up.
getting it?
No.
What are you seeing?
We were seeing the video, but not the audio that time.
Oh, you weren't getting the audio. Rats. All right, let me restart. Oh, it's because I had share sound on. Turn that off. Let's try again. I'll start already in progress here. So that's what it would look like to fly from Manhattan to the end of the Fish Pier, which happens to be owned by Massport, by the way. And I've already talked to them about operating off the end of the Fish Pier. So we hope to make that happen. Oh, and Jeff said he was getting audio. So that's interesting. I've had this problem where people have said if I share audio, they don't hear it. And now Jeff says he does hear it. So I'm sorry for the technology glitch.
Interesting.
Yeah. But let me share. I want to share another one that will show you the actual fifth scale in flight test. So this video I'm going to show you, I may skip through it a little bit because it's a bit long. It shows each maneuver from two views because this was a flight test. So you'll see it from a fixed camera and then from a roving camera view. And what this test was about was maneuverability testing in helicopter mode. We wanted to see whether the handling qualities that we projected from the design and from the X-plane simulation actually played out with a real flying aircraft. And again, this fifth scale is way big enough so that with appropriate mathematical corrections, we can derive real data about how the full scale will fly. So let me show you that. Just wait to see which screen it is.
And Peter, while you're looking at that, we do have a question where your flight test operation is.
It's based out of Carlisle, Mass. So just 2 towns over on the far side of Hanscom from me in Lexington. So yeah, we're headquartered up here right around Concord, Carlisle, Lexington. We've got a cadre of people in Connecticut, the Nutmeggers, and then a host of people across the world, really, consulting, contracting, and advising us. This flight test I'm going to show you took place in, this was in Acton, in a pumpkin field in Acton after the harvest. So, here's my zoom. Sorry for the delay. There it is. takeoff. There's the same takeoff from the other view. All of this is real time, by the way. That's testing pitch authority using the tail fan. Turn the music down a little bit. Now we're going to fly backwards and test some pitch authority. So that's a horizontal turn using the flaperons deflected in the slipstream. So there's that turn again. You know, I like the music, but I think my talking over it might be more interesting. So that was a left roll, and it started moving pretty fast. It has great authority in roll. And so there was a right yaw turn to a right roll. And so this looks like it might be slow motion, but like I said, this is all in real time. And the way it yaws is that the trailing edge devices, which would be ailerons in airplane mode, we refer to as flaperons because we use them as both ailerons and flaps. And in helicopter mode, when you deflect them, they generate yaw. And so here, I'm the test pilot for this. And so here I am flying backwards. And then we pitch forward to arrest the backwards motion. And the pitch moments are all coming from a fan in the tail that I mentioned. So the fan blows up or down as necessary to generate downwards or upwards pitching of the nose. And here's a landing. So it's a little faster than I wanted, so I caught it. It's actually a pretty good landing, if I do say so myself. You know, one of the things I realized about landing, you know, if you blow a landing, even after a great flight, it's like telling a joke and blowing the punchline. It just takes all the fun out of it. So here's the second flight. So take off, get a little bit out of the camera. And now we're going further downfield this time. There was a little bit of a wind, so what you saw there was me to yaw into the wind so I didn't get blown into the trees. And if you see standing down at the far end, there's a safety officer. That's Dick Gersh, who I'm sure a bunch of you know. So Dick is part of our program. And we've really benefited from his expertise from his Terrafugia time. All right, so we went downfield. We're doing a turn to come back. It's 270-degree right yawing turn. A little bit of pitch forward to catch some back momentum to the right that built up during the turn. And now we're going to do a little bit of a test of how maneuverable is it. So pick up some speed going forward. And then we're going to do yaw, roll, and fly around the corner here. So here's yawing sideways. Going to roll into that. See how fast it accelerated? It's like, whoa, better tilt the other way, pull the nose down, come around the corner. Yeah, when you've got both props, it doesn't take much roll tilt in helicopter mode to develop quite substantial translation rates with sideways speed in less geeky jargon, which is great actually for, again, technical terms, gust rejection. But because we have a lot of roll authority, if we get hit by a sideways gust, we can roll the aircraft into that gust and maintain positioning quite well. Maybe not exactly as well as a high-performance helicopter, but pretty close. And certainly well enough to meet the ADS 33 handling qualities tests that people use to assess the handling of rotorcraft. And so now I'm backing up and coming towards the fixed camera. So I'm backing up and actually translating right to starboard because I didn't want to land in some rotten pumpkins. So we're coming back, stopped going backwards. Now we're just going straight down. And there's the touchdown. And again, I thought this was a pretty good landing. The gear on this version of the prototype, by the way, are two 1/3 scale Piper Cub main gear linkages. So we got them from a big giant scale Piper RC model. So we've got another question from Jeff. How does the tail rotor change thrust direction? Variable pitch, yes indeed. Which in the rotorcraft world we refer to as collective. But yeah, the propeller in the tail can rotate, almost 180 degrees. So it can blow up or down, or sometimes we like to say that the tail fan both blows and sucks, if you'll pardon the language. So we're almost to the Q&A period, but I have one more video I wanted to show you. And that is one of the reasons we know this design is going to work is that back in the 60s, there was a bunch of research on tilt wings, and the most successful tilt wing aircraft was a Canadian aircraft called the CL-84, and it had a very similar planform to the Vi. In fact, you could really think of the Vi as the ultimate evolution of the CL-84, but we just get to benefit from over 50 years of technology advancements. So we've got higher temperature coatings for jet engines, better turbine blades, so much better power to weight in the jet turbines, so we can be one instead of having to have two like the CL-84 did, and the whole airframe parachute. But beyond that, computerized flight control systems. People have sort of feared tilt wings because one of the barriers to adoption they ran into in the 60s was achieving acceptable handling qualities through all phases of flight, including the transitions to and from airplane and helicopter mode. And we supposed at the beginning of this program that with computerized flight controls and individual actuation of all the control surfaces, again, the technical term for our aircraft is that it's over-actuated, because we can generate rolling or pitching or yawing moments using multiple control surfaces. So as you saw in helicopter mode, for roll, we actually use the propellers. With the electric aircraft, we speed one propeller up and we slow the other one down. With the full scale, we'll have collective pitch, adjustable pitch propellers, and they'll generate more or less thrust, and that's how you get a rolling moment. But in airplane mode, we use the ailerons for rolling moment, just like a normal fixed-wing aircraft. And in between, you have to go from one to the other, and it's called blending, and that the way you blend from one to the other turns out to be a trick. And it's a trick we've spent years mastering. And in the process, we've invented some new ways of controlling a tilt wing that were never done before, and are only possible because of this individualized flight control. But what I'm going to show you now is a little video I did where I took one of the standard demo videos that was shot in the late 60s of the CL-84, and I flew all those same maneuvers in our X-plane simulator just to demonstrate that our simulated Vi can do everything the CL-84 did. And as it turns out, it's going to be more. So let me share that real quick here, and then we'll take questions. I reused some of the same music.
With the wing tilted up, the power lever is advanced to make a vertical ascent to hover. As in all modes of flight, the aircraft is controlled by the stick, rudder pedals, and power lever. To fly sideways, the stick is moved sideways to command differential propeller pitch instead of aileron, as in conventional flight. The 84 can fly sideways up to 35 knots. To rotate the aircraft, rudder pedal movement controls the flap aileron, which, being immersed in the slipstream, provides the necessary yawing moment. This transfer of control authority is obtained by means of a mechanical mixing box in the control circuit containing a series of scans which rotate with wing tilt. In this way, a given control input is translated to a command to the relevant control function. A thumb switch on the power lever selects wing tilt angle. Here the wing is tilted beyond the vertical to put the aircraft into reverse flight while the fuselage remains level. The 84 can fly backwards at up to 35 knots. The ability of the aircraft to fly sideways and backwards is a measure of its ability to perform hover turns in a wind while remaining on station and handle crosswinds during takeoffs, transitions, and landings. 0 to 100 knots takes about 8 seconds. The flying demonstration concludes with an inbound transition to a hover landing. The relative movement of the horizontal stabilizer with the tilting wing is clearly seen. A small reduction of power is required to complete the landing as the aircraft enters ground effect.
right.
Peter, we've got a couple questions.
Excellent.
What does the dead man's curve look like for VY while in helicopter mode?
That's an excellent question. So for those not familiar, the dead man's curve, or less sensationally termed the HV diagram, the avoid area of the HV diagram, which stands for height velocity, is it's a curve in the POH for every single engine helicopter, as well as most multi-engine helicopters, because most of them, depending on their loading condition, will also have this. And so by avoid area, it's a range of forward airspeeds and altitudes that you want to stay out of, because if you lose an engine at that, you're going to crash. And if you crash high enough, of course, people may die. So, for example, the Bell 407 has an HV diagram that at max gross sort of intercepts zero airspeed at 800 feet. So if you're in a hover below 800 feet in a Bell 407 at max gross and you lose the engine, you may well crash, and it could be severe. So the VY has a similar shaped HV diagram in that we want to stay low while we pick up speed, and then once you have forward speed, in the case of a helicopter, you can translate that into a chance for auto rotation, where you can use the descent of the aircraft to spin up the rotor, and then you can turn that rotor RPM into some last-minute thrust and cushion your touchdown. With the VY, since with the parachute, forward motion actually helps us with extracting the parachute, which does two good things for us. It absorbs energy that doesn't have to be dissipated by the aircraft structure on impact, and it also orients the aircraft in a predictable way so that we know what the load paths will be when the aircraft crashes. And we're designing the aircraft structure to dissipate that energy just like your car does. In fact, we're using a lab at Kansas City University that actually is the world leader at doing this sort of structural deformation simulation analysis, along with BRS, to help us do the structural design for that. So what else we got, Keith?
We also had a question regarding how does the parachute deploy? I know you covered it briefly, but if you could do it again for us.
Oh, absolutely. So Boris Popov at BRS came up with this concept, and from the beginning they've used rockets to deploy the parachute. So if you look at a Cirrus, on the empennage, there's a panel, it turns out. It's painted over, you can't really see it. But there's a panel that gets blown out, and a rocket emerges and pulls the canopy up, where on the standard original version of the BRS parachute, the moving air, the aircraft moving through the air, would inflate the canopy. Now, they've actually announced, 2 years ago now, they announced a new variant of that where they use pyrotechnic inflators, similar to the inflators for airbags in cars. And the importance of that is it takes a bit of time to get the canopy inflated, and you're getting drag that whole time, which is helpful, but you really want the full canopy. And so the pyrotechnic inflators help with that. We don't have a hard number for you yet as to how low we could successfully deploy the parachute, but it's below what the old school SR-22 numbers were, which were somewhere around 1,000 feet of AGL. So it should be well below that.
That's interesting.
Yeah.
Next on our list is, can you describe what the controllability post-engine failure might be? Given the ballistic parachute system, will there be no flying it back to the ground?
Oh, that's an excellent question. And so it turns out that it's very important under Part 23 that after an engine failure, you can conduct continued flight to a safe landing, is the regulatory language. And then when you go and look into what that refers to, it's really controlled flight to a safe landing. And so there are two ways that we can have controlled flight under canopy, or two aspects to controlled flight under canopy. So this is not your standard Cirrus, which really does just descend in an uncontrolled way. So it turns out that if you tilt the wing of the VY backwards, and actually I have my briefing stick VY, if I hold it in front of my face, you'll be able to see it. If you tilt the wing of the VY backwards like this, which we can do, we can go to 110 degrees of tilt, so it looks like that, and the aircraft is descending under canopy, the uprushing air generates forward thrust, right? So the air is hitting the back of the wing, and the aircraft wants to fly forward. We have emergency battery power. All of our flight controls are electrically actuated. So if we lose main turbine power, we still have actuation of the flight controls. And so we can still use the flaperons to steer the aircraft. So we've got now we can point it and steer it and fly it under canopy. So that will be a controlled descent, under control of the pilot. The other aspect is if the wing was frozen, say there was damage and you couldn't tilt the wing, the canopy itself will have panels in the back of it that pop open, and the air flowing out the back of those will also generate forward thrust. So either way, we'll have forward thrust and steering. So the loss of the engine alone will still allow for a controlled landing.
Jeff asks, do you have a sense of what the max forward speed to hover transition time will be?
Yes. So I have done, so you saw those X-plane simulations, and we've benchmarked those against state-of-the-art. I mean, X-plane is a game, right? But it turns out that its physics model is quite sophisticated. In fact, I hosted Austin Meyer to present on the physics of X-plane, hosted by the Vertical Flight Society. And so if you're interested, you can go read about it. And what all the pros said, they're like, oh, it's a panel model or a strip model, where it's computing real physics. So you obviously can't believe it by itself. But when you add in other analyses and our flight tests with the real prototypes, we understand where it's telling us the truth. So it is in fact telling us the truth about how fast the aircraft accelerates and how fast it'll go through the transition. And I can tell you right now that from starting hovering over the numbers at 2.9, by the intersection with 2.3, we're fully transitioned and going over 150 knots.
Definitely impressive.
Yeah, I mean, way more than you would use with passengers. That's the peak acceleration longitudinally during that transition is 1.75 Gs. So you're feeling, 1 3/4 your own weight slamming you back briefly during that transition. So we would never do that in a passenger flight. But it is a very high performance aircraft. I mean, that's one of the fun things about a VTOL. It has to have a greater than 1 thrust to weight. And when you start using that greater than 1 thrust to weight in airplane mode, it'll outclimb any terrain. It'll climb straight up.
One of our longtime members showed up a little late this evening, and he's just asking if you could quickly describe the powertrain.
Absolutely. One more time. So the powertrain is a turboshaft engine, which is mounted here, abaft the wing. It's a turboshaft, so it has a 20,000 RPM rotating shaft coming out of it. That shaft enters a main T gearbox. So basically, you get a drive shaft out each side, so it looks like a letter T. So there are drive shafts that run down each wing with appropriate hangers and flexors and stuff to deal with the wing bending and changing shape for temperature and all that. And then we've got a planetary gearbox in each nacelle. And that planetary gearbox is the L gearbox, so the PGL gearbox. And that turns the corner up to the propeller drive shaft. And the prop is mounted to the nacelle, so all the load paths go through the nacelle. So that drive shaft is a torque-only drive shaft. So it's not taking any of the loads, bending, tilting loads from the prop on it. And then up into the propeller hub, and it's a fairly standard propeller hub, variable pitch propeller hub design. So it's a turbo mechanical drivetrain. Those gearboxes are not pushing any state of the art. We're lucky to have attracted a gearbox guru to do the design for us, a guy named Bob DeRusso. Bob was at one point in his career recruited by NASA to head a R&D committee about pushing the state of the art of helicopter gearboxes. But these are much simpler than what helicopters use. And much lighter, by the way. If you did a 600-volt electric system to distribute the power, we need most of a megawatt out of each propeller. If you did a 600-volt system, just the copper wiring in one wing would weigh more than our entire mechanical gear train. You have to use really big, heavy copper wires to send that much power around, as it turns out.
Ken asks, what are the attachment points for the parachute, and how does the parachute deploy helo versus airplane mode?
Well, so the attachment points, there'll be 2 of them forward of the wing tilt and 2 of them aft. They use Kevlar risers, and they're designed to be thick enough so that if a propeller blade struck them at full power, the propeller blade will break, the risers will not be parted. So that's safety. That's another safety measure. They're to hard points on the fuselage, and all the load paths have to be. We haven't finished the detailed design on that yet, but it's a very solvable problem. Cirrus has done this now. BRS has done this several times now. We're kind of most similar to the Vision Jet, of course. And like the Vision Jet, I expect that we'll program the flight control system to maneuver the aircraft into an optimal attitude for deployment, if we can. And if you can't, then you're just going to deploy it however.
Ken also asks, what is the range of prop rotational speeds? How does this change from helo to airplane mode?
So it uses a fixed RPM for both props at all times. The engine we have, in theory, has the capability to let us slow the prop by 10%. And I say in theory because we're still a little skeptical and we're working with the engine manufacturer on really assessing if that's going to be true. The point of that slowdown is that helps us optimize the propeller design for the high-speed hover trade-off. So right now our design points are hot, high, hover, which is 100 degrees at 5,000 feet, 100 degrees Fahrenheit, 5,000 feet, hover out of ground effect. So that's one design point for the power, for the propeller and for the power from the engine. And then the other design point is that 353 knots at 15,000 feet on a standard day. And hover efficiency makes you want to have longer blades, which gives you supersonic tip issues at high speed. So those oppose each other. If we can slow the rotation speed in airplane mode at high speed, we can actually go with longer prop blades and get better hover performance. We don't need it. I mean, the prop design we have now works for both, but it would be nice to have a little bit of extra margin.
Peter, thank you. Personally, I'm fascinated by this, and I learned a lot this evening. And we're going to leave with one last question. So the question that we have is, when do you foresee full-scale aircraft testing to begin?
Not before Q4 2022. If everything went perfectly, we would have a full-scale aircraft starting to fly towards the end of 2022.
Well, thank you very much, Peter. That was a great presentation. I think all of us were intrigued by that, and I certainly learned a lot. And we'll all be definitely following Transcend Air as you guys continue your development. And I'm sure, at some point we'll have you back again to give us an update. So that was great. Thank you very much.
Oh, my pleasure. Thank you guys.
And just with regards to a couple other things I wanted to mention with the Aero Club in general. I started at the beginning by saying we're going to return to some in-person events. Our first in-person event will be starting on May 22nd with our first outing, which will be a gathering, either fly or drive, to the Airfield Cafe in Nashua, New Hampshire. And we're also planning a fly-out event in June, July, and August, which the information on those will be forthcoming. Events that outings you can either fly or drive to, and those will be opportunities to also get together outside at various airport restaurant venues. So be on the lookout for those announcements. We're also going to have another virtual event in June, and the speaker will be Jim Baum, who's a member, and he's going to be talking about his experiences flying around the world in his TBM. And the date will be announced shortly. It's either going to be June 9th or 16th, but we're just finalizing that with the speaker, and we'll send out a notice on that shortly as well. So stay posted on that. Thank you guys all for joining us tonight. We appreciate it, and I hope you guys all have a great evening.